Hello everyone, hope you're doing well. My name is Runak and I'm here to narrow down some statistical concepts for you. If you're familiar with my channel, you know so far we talked about a lot of statistical techniques and we learned a lot. In today's video, we're going to learn how to run multiple linear regression in RStudio. We talked about simple linear regression in its tutorial previously. Now we will run multiple linear regression for the same example and the same data set. So the multiple linear regression is applied when we have more than one independent variable or features. I'm gonna open up the data set again for you to review it together. So this data set is about cases of coronary heart disease in a short form CHD. And we assume that we measured the bad cholesterol level or LDL and other variables associated with patients' conditions like systolic blood pressure, yearly tobacco use, adiposity, family history, type A personality score, obesity, which is measured by body mass index, alcohol use, age, and diagnosis of CHD. In the simple linear regression video, we only considered the relationship between systolic blood pressure and bad cholesterol level or LDL. But now we are interested in knowing the effects of more predictors besides blood pressure and the bad cholesterol level. So these independent variables are yearly tobacco use, obesity, alcohol use, and age. So basically, we want to see the relationship between bad cholesterol level or LDL and the use of tobacco, obesity, alcohol, and the age of these cases. Before going forward, we first need to check the assumptions that are needed to be met before doing the actual analysis and running the multiple linear regression. So in addition to the dependent variable being a continuous quantitative variable, the first assumption that needs to be met is linearity. That means that there is a relationship between the independent variables and dependent variable that should be linear. And the second assumption is independence, which means observations must be independent. Third assumption is normality. The residuals must be normally distributed. The fourth assumption is the homoscedasticity, which means the variances of the errors should be constant. Then there should be no violation in these variances. And the last assumption is not having any outliers. So let's get started. First, we need some packages to be called or installed. So if you don't have these packages installed, you can simply do that by install.packages command. Then we load the dataset and save it as data. Then use dim and head functions to look at the basic structure of the dataset. So run it. You see in the console window, we have 462 observations or cases or patients and 10 features or variables. And by head function, we've got the first 6 rows of all these features. So in the next step, in order to check the assumptions, we need to define the model first for visualizations. And to do that, we use lm function to define it. Let's name the model MLR, short form for multiple linear regression. Then we first type the dependent or target variable, which here is LDL, then tilde to fit the model. And next, the independent variables on the right side of the tilde, and add them at any order you wish. As I said, I think 20 times so far, our independent variables are tobacco, obesity, alcohol, and age. And finally, specify the dataset that you want to take these variables from. For now, we check the assumptions first, and then we will be back to interpret these results of the model. We know that observations of this data set are individual people, that one person's condition did not have effect on another person. So it shows that these observations are independent. So the independence assumption is met. So for remaining assumptions of linearity, normality, homoscedasticity, and finding outliers, we're simply going to use plot function to visualize them, because this way is more engaging and you can grasp it in a second. So before that, to make the plots look better with a better layout, to get them in just one output, we use par function, which stands for parameters. So now simply use plot function for the model, and it'll give us 4 plots pop up in plots window. Here, first graph is residuals vs fitted values, which is checked for the linearity. We say we have a linear relationship if the residuals are spread equally around a horizontal line without distinct patterns. So you see for our model, the dots are equally scattered around this line. There is no pattern, or at least I don't see any patterns for this data. So we can say that the assumption 1, which is linearity, is met. The second assumption is a normal QQ plot, and it is used to check the normality of residuals. If the majority of the residuals follow the straight dashed line, then the assumption is met. So as you can see, for this example, we could say that the residuals are almost normal. And the third graph is called the scale location, which is used to check the homoscedasticity of residuals or equality of variances of residuals. So how do we know if this assumption is met or not? If the residuals are spread randomly, then the assumption is met. Here we see that this matter is fulfilled. So this assumption is also met. Move on to the last assumption, which is residuals vs leverage graph. And it is used to identify outliers. Outliers are extreme values that might influence the regression results. So as you can see, there is no high leverage point in the data because all the data points have a leverage statistic below 3 standard deviation of our model. 3 standard deviation of our model is 0.3 here, and you see all of them are below, and that was it. They are all met. I just want to say that you could have used the box plot to see the outliers, but we get them at once in one graph, so it is much easier to use this graph of residuals vs leverage values. So anyway, now we're good to go and see the summary of our model and interpret the results. To get a summary of the model, simply use the summary function. And yeah, you see the output here in the console window. We have got the coefficients, p-values, test statistic, r-squared, and adjust r-squared. But I think it would be nicer if we could tidy them up a little bit more. So we use tidy function and run it. You see these results are red because they're less than 0. And you can use RSQ function to get the r-squared that we lost from tidy function. You see the result again here in console window. Also, a way better output could be gained by TBL_regression function. As you can see, this table is ready, organized, and much prettier. It contains coefficients, confidence intervals of 95% and p-value for each. but there are no statistic of the test anymore. So anyway, now let's interpret the results. First, we need to examine the F statistic and the associated p-value from our first output. Scroll up and you see the p-value of the F statistic is 2.2e to the power of negative 16, which is a very small number and way less than 0.05. So we conclude that this amount is significant and we reject the null hypothesis. This means that at least one of the predicted variables is significantly related to the outcome variable, which in this case is bad cholesterol level, or LDL. To see which variables are significant, we look at the coefficients table. In each of these outcomes, it doesn't matter because either the first output or the second one, they both are the same and gave us the same estimates of coefficients and their associated t-statistic p-values. Remember that I said this last table wouldn't give us the t-statistic value, but it's okay, we can handle it by what we have got so far. As you can see, for each of these independent variables, the t-statistic evaluates whether or not there is a significant association between this variable and the outcome variable. Or put it another way, based on the hypothesis, we say that whether the beta coefficients of the predictor is significantly different from 0 or not. As I said a million times, we have 4 predictors: tobacco, obesity, alcohol, and age. And from the result, it can be seen that different BMI levels and different ages do have different effects on LDL or bad cholesterol level. In other way, out of these 4 variables, obesity and age have a relationship with the bad cholesterol level. That was it for now. But in the next step, we want to learn how to formulate this multiple linear regression model. We have the formula for multiple linear regression here. White hat here is LDL. We write it down, LDL, equal with the intercept, 0.0451 plus beta 1, 0.02 multiply tobacco, plus 0.13 multiply obesity. And because beta for alcohol is negative, we just simply write down minus 0.01 multiply alcohol and 0.03 multiply age. How do we interpret this equation? It's easy. Just listen to me. Based on this equation, considering holding all other predictors constant, we can expect that 1 unit increase in BMI index or obesity causes 0.13 millimoles increase in bad cholesterol level, and 1 year increase in age causes 0.03 millimoles increase in bad cholesterol level. And that was it. For 2 other variables, tobacco and alcohol, we say that changes in the level of these 2 will not significantly affect the LDL or bad cholesterol level, and we can even remove them from the model. So now move on to the last step, which is the interpretation of R squared. In multiple linear regression, the R squared represents the correlation coefficient between the observed value of the outcome variable, which is y, and the fitted value of y or y hat. And as you may know, an R squared value close to 1 indicates that the model explains a large portion of the variances in the outcome variables. And if it's closer to 0, it is not that good. Here R squared is 0.16, which is not big. And I think it's because we didn't bring all the variables of the data set into the model. We would have got a better model if we did that and considered all of the other variables into our model. So anyway, that was it. And I'll see you in the next video. Bye.